Question 1 then here is the setup. And before you can do any of the calculations, you need to process the raw data. So we've got this alcohol, 2-methyl cyclopentan 1-ol, being burnt in a spirit burner, and the heat from the flame is being used to heat this water in the pot there. So you need to know the mass of the water, which means you have to subtract the water plus the pot, take away the empty pot, which gives you that is the mass of the water. Similarly, to get the mass of the alcohol that was burned, you have to subtract the mass after burning from the mass before burning, which is these two numbers, and the difference is the mass that was lost as a result of the burning. And we have to find the temperature rise, delta T, which obviously means you just have to subtract the temperature at the beginning from the temperature at the end. So those three numbers are all crucial, and you had to realise that you needed to process those first. So in part A, it asks us to calculate the amount of heat that was released by the reaction. And the key to that is always this equation. Okay, Q is equal to MC delta T. And it's really crucial that you know what these three terms are. So delta T is fairly obvious, is the temperature change, which can be positive or negative, and at this point we're ignoring that. We're just looking at the size of the temperature change. We'll worry about the direction of it later. C is the specific heat capacity, and it's the specific heat capacity of whatever is soaking up the heat, which in this case is the water. And in fact, in A-level questions it's virtually always water, because it's either water being heated by a flame, as in this experiment, or water as a solvent being heated as a result of a reaction of the stuff dissolved in it. So C is nearly always the specific heat capacity of water. And likewise, M is the one that causes trouble. So M is mass, but don't just learn mass. It's the mass of the material being heated or cooled if it's an endothermic reaction. So heated or cooled. Not the mass of stuff reacting. That's the important thing. So in the context of this experiment, it's this mass, the mass of the water, not the mass of the fuel, because the heat isn't going into the fuel. This stays cool, the heat's all going up here, so it's the water that's soaking up the heat. Okay, so having established that, then it's straightforwardly a matter of putting the numbers in. So you say that's equal to 301.34 times 4.18, which comes from your data sheet. Always remember that the specific heat capacity of water is there on your data sheet, times 37.5, which is delta T, which we'd already worked out, which comes to 47235 joules. It's very important though to read the detail of the question, because that's not the answer, because it asks for it in kilojoules and it asks for it rounded to three significant figures. So kilojoules, remember there's 1,000 joules in a kilojoule, so the number of kilojoules you divide by 1,000. So you say that's equal to 47.2, and that's it, because three significant figures we're going to cut off there. That number is less than 5, so that just rounds to 47.2 kilojoules to three significant figures. In B, it wants an equation for the reaction. Now it already gave you the molecular formula just to make life a bit easier. So C6H12O, that was in the question. And we're going to assume that we get complete combustion. It doesn't exactly say that, but it does say to make sure your equation is consistent with the definition of enthalpy change of combustion. And remember, that does require complete combustion. Enthalpy change of combustion is the enthalpy change on 1 mole of a substance, so we can only have one of these. Burns completely, which means burns to produce carbon dioxide and water in oxygen. So we're going to have some O2s there, and we'll work out how many in a minute. But we know that we're going to get 6 carbon dioxides because we've got 6 carbons. And we know that we're going to get 6 waters because there are 12 hydrogens, 2 for each water, so 6 H2O. So all that we have to find now is the number of oxygens. So we've got 6 2s are 12 there, plus another 6 makes 18 oxygen atoms on the right, so we must have 18 on the left, and the crucial thing is to notice that one of them is already there. And that's the common mistake when you have burning equations for alcohols, that the risk is you forget the one that's already there. So we've got to find 18 altogether, but one's already there, so we've only got to find 17, and that's 8.5 lots of 2. So that's your equation, and it's got to stay like that. If you feel tempted to double everything to get rid of the half, normally that would be fine, but not now, because it said that it had to be compatible with the definition of enthalpy change of combustion, and that says when you get complete combustion of 1 mole. So you've got to live with the half in this case. In part C, it wants to know how many moles of the alcohol were burned. So we've got the mass, 1.60, so we can just do moles is mass over mR, which is 1.60 divided by, and if you add up the mR for that lot, it comes in fact to exactly 100. So that's 0.0160 moles is the answer. And then it wants us to use these numbers that we've calculated so far. So we've got Q up there, and we've got the number of moles here, and we can use those now to find delta H. So the way we do that is to remember that delta H is going to be negative, and the reason it's negative is because it's exothermic. In other words, the temperature went up. Okay, and it's important, I think, to explain why you're making it negative. If the temperature had gone down, it wouldn't have changed the calculation earlier on, but it would change the sign now, and we would have made it positive. So because it's exothermic, and the reason we know it's exothermic is because the temperature increased. Okay, so make sure you're clear, that's where that negative sign is coming from. And delta H is minus, you can get it from the units because you know it's going to be in kilojoules per mole, which is just kilojoules divided by moles. And if you just think of it like that, it makes it very easy to get the definition right, because you're basically just repeating the units. But you think, right, what's the number of kilojoules? Well, we've worked that out. So it's minus 47.2 divided by the number of moles. Well, we've also worked that out. And if you compute that, you get minus 2950 kilojoules per mole. If you use the unrounded number here, you get a slightly different number, but it still rounds down to that when you round to 3 significant figures. So very exothermic, but that's what you expect for a burning reaction. In part E then, it's asking us about a variant of the experiment where you do basically the same thing, but this time you burn 3.20 grams of alcohol instead of 1.6, and you heat a different amount of water, 602.68 grams instead of that. Now what you had to notice is that this is double the original quantity, and that's also double the original quantity. So these are not just random alternative numbers they've come up with, they've deliberately doubled both of them. So the key to this question is to start with Q is equal to MC delta T again, and then the question is, what's the temperature rise going to be? Okay, so you've got to rearrange that equation to get what delta T is equal to. Okay, so whatever it's asking you to focus on, what's the temperature rise in this case, you rearrange the equation to get an expression for that. So that means that delta T is equal to, so we've got to move MC over to the other side, and it slides diagonally across like that. So delta T is equal to Q over MC. So how is that going to change? Well, as we said, the mass of the alcohol burned is twice the original amount, because 2 times 1.6. So that has been doubled compared to the original amount. And if that wasn't obvious to you, then just do it on your calculator. Just divide that number by that number and get the factor that you've changed it by. But in this case, that it's doubled. And obviously, each mole of alcohol gives a certain amount of energy. So if you double the number of moles, which you're obviously doing, if you double the mass, then you double the amount of energy. It's as simple as that. So the amount of energy given out will be doubled because we're burning twice as much. And just common sense tells you that. You know, if you burn 2 sugar lumps, you get twice as much energy as if you burn 1 sugar lump. It's the same as that. So Q will be doubled because there's twice as much alcohol being burned. C is the same because that's the specific heat capacity of water. That's an intrinsic property of water, so that was no different than in the original experiment. But M, remember, is the mass of the water heated, and that was also doubled. Okay, because 602.68 is exactly double the amount of water. So what have we done? We've doubled the top line, but we've also doubled the bottom line. Okay, so top line and bottom line both double. Which means that delta T stays the same. Okay, because if you double the bottom line and you double the top line, the two effects cancel each other out, and so delta T stays the same. So that would be fine as your answer, but or you could put the number down, 37.5 degrees C. Okay, so Maurice does this experiment, he gets his number for delta H, and then his friend comes along and says, yeah, but that doesn't agree with the books. It doesn't agree with the standard enthalpy of formation, of combustion, which you can look up you know, in the database, and you don't get the right number. And it's asking you for suggestions as to why not. Now, when you get those kind of questions, what you can't do is suggest that he made a mistake, you know, he wrote down the mass wrongly or something like that. In real life that might well be true, but what they're looking for is actual flaws in the design of the experiment, not kind of incompetence in the way it was carried out. They will never give you credit for that. So what are the flaws in the design of the experiment? The big one, the one that really makes this experiment rubbish unless you take a lot of precautions, is that it's clearly absurd to assume that all of the heat from that flame is ending up in the water, because some of it is going to be heating up the pot. If you choose the right kind of pot, you can make that small, because if it has a low heat capacity, that's not a big deal, but it's going to make some difference. But you're going to get heat escaping into the surroundings. That's the big one. So that's I mean, it doesn't matter, they would give you the marks for any of them, but in real life that's the big one that you need to worry about. So heat loss to the surroundings. In other words, not all the heat released is taken up by water. And of course the effect of that is that Q is underestimated, because when you calculate MC delta T is smaller than it would have been if all the heat had gone in there, so Q is underestimated, and therefore delta H comes out less negative than it should be. So that's the first one. Other things you might think of, one of them is that you may not get complete combustion. And remember, that doesn't mean not all the stuff will burn. We know not all of it burns, only 1.60 grams does. It means that when it burns, it doesn't necessarily produce carbon dioxide. Some of it might produce carbon monoxide or even carbon, so may not get complete combustion, meaning that the reaction wasn't simply the one you wrote in the equation, that some of the molecules ended up doing something different, producing carbon monoxide or carbon. Those reactions are less exothermic. So again, if that were the case, you would have underestimated delta H of combustion. So that's the second one. Another one is that it's possible that some of that loss of mass was actually due to evaporation, you know, before you lit the flame. Or whatever, you know, between weighings, and so some of the alcohol may have been lost by evaporation rather than combustion. It's not likely to be a big number, but it's a possible one. So some alcohol could have been lost by evaporation rather than combustion. And the fourth possibility is that conditions were not standard. in the experiment. The pressure may not have been exactly 1 atmosphere, but it probably wasn't very far off, because it was, as far as we know, done at atmospheric pressure. But the temperature, the reaction's happening in the flame there, and the temperature clearly is not 25 degrees C. So temperature is not 25 degrees C. And that's going to mean that delta H could in principle be different. The biggest reason it's likely to be different is that the water is formed initially as steam, because obviously the flame is very hot. Rather than liquid water, which is what it would be under standard conditions, because standard conditions, remember, is 25 degrees C, where water would be a liquid. So that's going to make quite a significant difference. Okay, so those are all reasons why you wouldn't expect to get it exactly right. So measuring really accurate enthalpy changes of formation, you have to take all kinds of precautions to make sure that none of these things are true, and you can't do that with simple kit like that. So you need to know this. Okay, this wasn't just a random question that I made up to get you thinking. These practical aspects are things you're very likely to get asked about. So make sure you understand why these are issues and make sure you remember them.